Welcome to The Explainer. Today, we're unpacking the invisible force that literally dictates how every single device in your life operates. I mean, everything from that tiny microchip in your smartphone to the massive power lines stretching across your city. We are talking about the friction of electricity.
Let's jump right into this with an analogy I think we can all relate to. Imagine you're riding a bike down a perfectly smooth, freshly paved road. Your pedaling feels effortless, right? But the second you veer off into thick, sticky mud, you immediately lose speed. You have to push way harder just to keep moving forward, while you're experiencing physical resistance.
And just like that deep mud resisting your bike tires, literally all matter exerts a certain level of what we call electrical resistance against the flow of electricity. It's basically a measure of how difficult it is for an electric current to travel through a material. Because, electricity doesn't just flow completely unimpeded, it actually has to fight its way through the atomic structure of whatever it's passing through.
This completely explains why insulators, things like plastics and rubber, act exactly like that thick mud. They have incredibly high resistance, so they pretty much block electrical currents from getting through. On the flip side, metal conductors, like copper, they're your smooth asphalt. They have very low resistance, letting currents zip right through with almost no effort at all.
But here's the thing, resistance isn't always some bad guy we need to defeat. It's actually a super useful tool. Engineers use specific components called resistors to purposefully control current flow. Say you're wiring a home theater. You want low resistance so a massive current can hit those speakers and blast your music. But if you're dealing with delicate little circuit board traces, you absolutely need high resistance to limit that current, or else poof, those traces would instantly vaporize.
Section 1. Unlocking Ohm's Law, the rules of the universe. So, how do we actually calculate this? It all comes down to the foundational work of a scientist named George Simon Ohm. He discovered this massive, fundamental rule. As the voltage applied to a resistor goes up, the electric current increases right along with it, proportionally. And that relationship, that's the electrical resistance, measured in a unit named right after him, the ohm.
To easily lock this into your brain, just remember the mnemonic VIR. Seriously, think of it as very important resistance. V, which is voltage, equals I, your current, multiplied by R, your resistance. VIR. It's beautifully simple, but this one equation is literally the absolute bedrock of modern electrical engineering.
Okay, let's put this into practice. Imagine we're analyzing a real circuit. We know our voltage is exactly 25 volts, and our meter is showing a current of 410 milliamps. But we have no idea what the resistance of the attached load is. How are we going to figure that out using Ohm's law?
Well, let's do the math. The crucial first step, and honestly the one people always forget, is getting our units right by converting those milliamps into standard amps. So, 410 divided by 1,000 gives us 0.41 amps. Next, we just rearrange our trusty VIR equation to isolate R. We divide our 25 volts by 0.41 amps and boom, we get 61 ohms. We just mathematically solved our invisible puzzle.
Section 2. The thermal energy problem. Now, we've been talking about resistance as a helpful tool, but when we zoom out to the big picture, like transmitting power across the country, it becomes a monumental engineering nightmare. See, even the very best metal wires have some innate resistance, and as electricity battles its way through miles of power grid, that friction generates heat. That's not heat keeping your house warm, that is pure, wasted thermal energy bleeding right into the atmosphere. It's a massive drain on our global energy efficiency.
Section 3. Superconductors to the rescue.
So, how on earth do we fix this? How do we beat the friction of the universe? Enter the holy grail of electronics, superconductors. These are special materials that don't just lower resistance, they drop it to absolute zero. Literally zero electrical resistance. If you build a wire out of a superconductor, energy travels through it with 100% efficiency. Not a single drop of power is lost to heat. It's almost like magic.
But yeah, there's always a catch, right? The massive hurdle here is extreme cold. Early on, we had to chill these materials with liquid helium down to a freezing minus 269 degrees Celsius to see this work. And obviously, wrapping our city grids in liquid helium just isn't going to happen. But materials science is pushing the limits. We now have materials like Hg1223 that only need to be cooled to minus 135 degrees Celsius. The ultimate dream? Finding a superconductor that works at regular, everyday room temperature.
And even with those crazy freezing requirements, we aren't just sitting around waiting for the future. Superconductors are actively powering some insane tech right now. Those giant MRI machines at the hospital, they rely entirely on superconducting coils to generate their magnetic fields. Same goes for massive scientific marvels like the Large Hadron Collider, using superconductors to literally smash particles together at the speed of light.
Section 4. Measuring electrical resistance.
Okay, let's bring it back home. Say you just need to figure out why your favorite lamp stopped working. For that, you need an ohm meter. This is your essential diagnostic tool. It's brilliantly simple. It pushes a tiny, known current through a component, does the Ohm's law math internally, and instantly tells you the exact resistance of whatever you're testing.
Now, I literally cannot stress this next part enough. Safety first. You absolutely never, ever use an ohm meter on a live powered circuit. If the electricity is still flowing when you hook that meter up, you're going to destroy the tool or worse, get seriously hurt. So, step 1, turn the power off. Once it's completely dead, then you connect the meter in parallel to your load and you safely read the resistance.
So what are you looking for? Well, a working light bulb or motor will give you a pretty predictable low resistance reading. But if you test it and the meter says off the scale or gives you an infinite error, you instantly know you've got a bad connection. It means the test current literally cannot get through. The wire is snapped, the element is blown, the device is broken. It's the ultimate, yep, it's dead confirmation. To wrap up this explainer, I want to leave you with something to really chew on. Imagine a future where our computers never need cooling fans and our entire global power grid operates with zero wasted energy. How radically would that change our world? We started off talking about electricity fighting through mud, but if we finally crack the code of room temperature superconductors, that mud completely vanishes. Keep that in mind the next time your smartphone gets a little too warm in your hands. Thanks for hanging out with me for this explainer, and I'll catch you in the next one.